Swayam Prabha. Digital India. Educated India.
Okay, I guess we'll get started with today's class, right? So if you recall what we did yesterday, right? So we were looking at a case study of a gear transmission, right? So where there was an input shaft to which a torque was provided, and the input gear was meshed with an output gear, and that in fact drove an output shaft, right? So what we did was that we derived the equation of motion using physics, right? And then we took the Laplace transform, applied zero initial conditions, then we got the transfer function of the system, and we figured out that the transfer function of was of order 2, right? So and the planned transfer function had a pole at the origin, right? So consequently, we are interested in designing a closed loop feedback control system that would stabilize the closed loop system, not only stabilize it, but also like satisfy these performance requirements of the settling time being less than 2 seconds and peak overshoot being less than 10%, right? Okay. So that's where we stopped yesterday, right? So now let's complete the design process today, right? So let's say, like I want to design a controller first to satisfy performance, right? Let's say we get started with that. Okay, so our planned transfer function, we just took it to be 2 divided by s times s plus 10, right? So that was our planned transfer function. Okay, and then the question is, what do we choose for the controller transfer function, right? So that we can get the process started. Okay, so to begin with, like let's say we choose the controller transfer function as just a proportional controller, right? So let's say the controller to be a proportional controller, so the controller transfer function just becomes Kp. Okay, so once the controller transfer function becomes Kp, this immediately implies that the closed loop transfer function is going to be y of s divided by r of s. That's going to be 2 Kp divided by s times s plus 10 divided by 1 plus 2 Kp divided by s times s plus 10. Okay, so I'm sure by now we are familiar with how to calculate this. This is like g of s divided by 1 plus g of s h of s, right? H of s is unity, g of s is c of s times p of s. Okay, so that's what we have. So consequently, the closed loop transfer function becomes s square 2 Kp divided by s square plus 10s plus 2 Kp, right? Now, what values of Kp do you think would make the closed loop system to be stable? So immediately we can realize that the closed loop closed loop, right? Characteristic equation is going to be s squared plus 10s plus 2 Kp is equal to 0, right? So this is a second order polynomial, and we know that for the two roots to lie in the left of plane, we need all coefficients to be non-zero and of the same sign, right? For a polynomial of order 2, that's something which we have discussed. So this implies that Kp has to be greater than 0 for closed loop stability, right? So that's something which we can immediately figure out. Okay, So for stability of the closed loop system, like we need the proportional gain Kp to be positive. Okay, so that is the condition, right? But that's not the only thing what we are expecting, right? So we are essentially expecting performance requirements also, right? So the question becomes, how do we then choose Kp such that we satisfy the two performance requirements, right? So we see that the proportional controller works as far as satisfying closed loop stability is concerned, right? Now let's look at performance. Okay, so consequently, if Kp greater than 0, works. Okay, so we consider the open loop transfer function g of s h of s to be 2 Kp divided by s times s plus 10, right? Kp is greater than 0. Obviously, why Kp is greater than 0? Because that's when we have closed loop stability, right? So we only consider those cases where Kp is greater than 0, right? So now we need to design for performance, and this is where we are going to use root locus to our advantage. Now you can see that we have set up the problem such that we can construct the root locus, right, for the closed loop poles, right? So Kp is a parameter which is positive, so we know what to do, right? This is negative feedback. We have already studied all the steps to construct the root locus. So what will the root locus give us? It will give us the locus of the two closed loop poles as we vary Kp from 0 to infinity, right? So now the question becomes, what range of Kp would satisfy the two performance requirements, right? So if you look at the performance requirements, the settling time being less than 4 seconds, if you compare it with that of an underdamped second order system, that means that 4 by zeta omega n should be less than 4, or zeta omega n should be greater than 1, or in a sense, we can say that, look, I want the real part of the pole to be less than minus 1, right? Oh, okay. So, okay, we wanted 2 seconds, right? Sorry about that. So we wanted 2, so zeta omega n should be greater than 2, and minus zeta omega n should be less than minus 2. Am I correct? Okay, so that's what we chose in this particular problem. Okay, so then if you recall, maximum peak overshoot less than 10%, we have already done a problem, right? So where we did this, and that gave a constraint on zeta, right? And then it once again led to a constraint on the angle beta. Do you remember? Can you tell me what that was? We already did this problem, right? So MP less than 10% means, please recall, e power minus zeta pi divided by square root of 1 minus zeta squared should be less than 0.1, right? So this gave us zeta should be greater than, I think if I recall vaguely, it was around 0.591 or something like that, right? So this implied that the angle beta should be less than some 53.76 degrees, right? That's what we had. Okay, so that's how we can convert the performance specifications into regions in the closed loop plane, regions in the S plane that we want. So let me draw the S plane, okay, and then we will start plotting these regions. Okay, so let's draw that. So this is the real axis, this is the imaginary axis, this is the S plane. Okay, this is the origin. Now let me draw the two desired regions. Okay, so let's say this is minus 2. So what happens is that if I draw a vertical line at minus 2, okay, so that gives me the boundary for settling time performance. Then if I draw two lines with that make an angle of 53.76 degrees, right. This angle is 53.76 degrees. That gives me the condition on peak overshoot, right. So, this is something which we already discussed. So, the net feasible area then comes out to be like let me draw it in a different color, let us say we choose green. Okay. So, the net feasible region for us that will satisfy both performance conditions will be this open trapezoidal region, right. So, whose boundary I am drawing in green color. Okay. So, that is what it is. Okay. So, that is where I want our closed loop poles to be. Now, let us figure out what values of Kp would do this job, right. So, that is what we want to do, right. So, let us start our analysis, right. So, our open loop transfer function is this, right, 2 Kp divided by S times S plus 10, right. So, let us start constructing the root locus, right. So, let us construct the root locus. Okay. So, step 1, what is the first step? You locate the open loop poles and open loop zeros in the S plane, right. So, where are the open loop poles? There is one open loop pole at the origin, and let us say this is let us say not really minus 10, but let me extend it a little bit. Okay. So, let us say I mark minus 10 here. Okay. So, minus 10 here is here, right. So, consequently the value of n is 2, the value of m is 0. There are two open loop poles at 0 and minus 10. There are no open loop zeros, right. So, correct. So, that is a first step. Okay. So, please remember our open loop transfer function, let me write it here once again on top. G of s h of s is going to be 2 Kp divided by S times S plus 10. Of course, we are considering Kp to be positive, right, because that condition came from closed loop stability, right, requirement of closed loop stability. So, let us go to the next step. So, what is the next step? So, step 2 is to determine the regions of the root locus, the regions of the real axis that lie on the root locus. So, for that like let us look at the real axis, we can immediately see that the real axis is divided into 3 regions, minus infinity to minus 10, minus 10 to 0 and 0 to infinity, right. So, now what is the test that we need to adopt? You choose a test point in any of the one of the regions, look to the right of the test point, the number of real open loop poles and real open loop zeros should be odd, right. So, if you take a test point in the region minus infinity to minus 10, you look to the right, okay. Let us say you take a test point here, let us say we call it as ST1, and you look to the right, how many real open loop poles and open loop zeros do we have? We have 2, right, that is an even number. So, this region does not lie on the root locus. Now, if we repeat considering a test point in the region minus 10 to 0, take a test point and look to the right, you have 1 open loop pole on the real axis, right, to the right. So, that is going to be odd, right. So, let us say you take a test point somewhere here, wherever we want, right. So, and you look to the right, you see that we have 1 real open loop pole to the right, that is an odd number. So, minus 10 to 0 will lie on the root locus. Then we take a test point in between 0 to infinity, let us say we call it as ST3, you look to the right, there are none, right. So, there are no open loop poles or no open loop zeros to the right on the real axis of any test point in this region. So, the only region of the real axis that lies on the root locus is the one between minus 10 and 0. Okay. So, that is what we have, right, as a second step. Is it clear? Okay. So, then we move to the next step. So, what is step 3? Step 3 is essentially figuring out asymptotes, right. So, we are going to have n minus m, which are essentially 2, which is the number is 2 here. So, there are going to be 2 asymptotes, right, in this particular problem. So, the angle of the asymptotes, or the angle made by the asymptotes, right, with the real axis is going to be plus or minus 180 degrees times 2k plus 1 divided by n minus m, alright. So, that is what we have. So, in this case, since n minus m is 2, so we can immediately see that this is going to be plus or minus 90, okay, or we can write it as 90 degrees and 270 degrees, okay. So, depending on how we want to write it, okay. So, that is what we want to have, and not only angle, but also the point of intersection of the asymptotes is something which we need to calculate. So, the point of intersection of the asymptotes, that is going to be sum of open loop poles minus sum of open loop zeros divided by n minus m, right. So, open loop poles, the sum is going to be 0 and minus 10, and open loop zeros there are none. So, divided by n minus m, which is 2, and the number happens to be minus 5, alright. That is going to be the point of intersection of the asymptotes, right. So, let us go here. So, let me just erase all these things. Oops. Oh, I think I'm sorry about that. I didn't expect this to happen. So, let us just go and mark these things, right. So, let us say minus 5 is somewhere here. So, what is going to happen is that there are going to be 2 asymptotes. One is going to just go at plus 90, alright, all the way up, and one is going to go at 270 degrees or minus 90, okay. So, those are the 2 asymptotes, right, as k tends to infinity. So, as k tends to, or kp tending to infinity, this is the direction in which the root locus branches would be going, right, would tend towards, okay. So, that is step 3, okay, of the construction of the root locus, okay. So, then let us go to step 4. So, what is step 4? We have to figure out whether there are any breakaway or break-in points, right. So, how do we figure out whether there are any breakaway or break-in points? We look at the open loop transfer function. So, immediately you see that the polynomial a of s in this case is going to be 2, that is it, right, because why? Please note that g of s, h of s, we need to write it as k times a of s divided by b of s. Of course, in this case kp, right, because that is what we are calling it as. So, kp times 2 divided by s times s plus 10, right, that is our open loop transfer function, right. Open loop transfer function is 2 kp divided by s times s plus 10. We have to keep kp away, right, because the structure is the constant or the parameter k times a of s divided by b of s. So, a of s is going to be 2, b of s is going to be s times s plus 10, right. So, consequently a prime s is going to be 0, b prime s is going to be 2s plus 10, that is what we are going to have, right. Okay. So, this will lead to the following, right. So, we need to solve the equation a prime s b of s minus b prime s a of s equals 0. So, this will just give us minus 2 times 2s plus 10 equals 0, right, that is what we will get. So, this will immediately give us a potential breakaway point at minus 5, okay. So we are not done yet. As I told you, like we need to find the value of the constant or the parameter, not constant, the parameter in the open loop transfer function. This is Kp here. So the value of Kp at S equals Sb, that's going to be minus B of S divided by A of S evaluated at S equals Sb. So what is this going to be? If you substitute minus 5, we will get minus 5 times 5, right? S times S plus 10, right? Am I correct? And divided by 2. So this will come to be 12.5, right? So, and that's greater than 0, right? So this implies that Sp equals minus 5 is a breakaway point. Why am I calling it as a breakaway point? Once again, it's pretty simple by now, right? So please note that. See, for example, let's say like I am plotting the final root locus, let's say in red. So please note that one branch will start from this open loop pole at minus 10, and it will start traveling to the right. Okay, why? Because the left, it can go to the left, right, as we know from step 2. And similarly, another branch will start from the open loop pole at 0 and start traveling to the towards the left. And obviously these two things will come and meet at minus 5. So minus 5 becomes a breakaway point where Kp is 12.5. Okay, so that's what we have as a breakaway point. Yes?
Poles and zeros are alternating, then there are no breakaway in
May occur, may not occur. Okay, so it depends on the problem. Okay, so if you have alternating poles and zeros, okay, but if you have complex conjugate open loop poles, right, and depending on the relative order of the system, values of n and m, you may have asymptotes going on the real axis, right? So you may have. Okay, but if you have open loop zeros, certainly some of the branches will terminate at the open loop zeros as k tends to infinity. Okay, so that's something which we need to remember. Okay, it really depends on the problem under consideration. See, another reason is that like why I am doing only like problems till order 2 in class is because of the algebra. See, if I can construct a higher order system to essentially demonstrate your points, but then like you will see that the computations will become complex, right? Here my primary purpose is to introduce the concepts to you so that like, and also we work it out using simple problems to begin with. And as you go along, you will see that the problems will become tougher and tougher. In your homework, you may get tougher problems for which you can make use of the help of some computational tools also. That's fine, right? So, but there can be various cases. Okay, yeah.
Value of Sp can be complex.
You mean the breakaway point?
Yes.
So if you have a what is a breakaway point in the complex plane, still you need to check the value of k. Okay, if you have k to be positive, then it's a potential breakaway point, right, or break-in point. But then we need to remember one thing, right? If you have a complex root, the conjugate also must be a root. So we are talking about a very complex situation, like where you have branches just intersecting in the complex plane, right, and then like going away. Let me maybe construct an example for that and then like show it to you, right? Yeah, but yeah, I think maybe I will construct a transfer function and give it to you. Maybe you can use MATLAB to construct the root locus and see for yourself. Okay. Yeah.
So what is the meaning of breakaway point in the complex plane? What does it mean? Like here we know that it diverges from the real axis. What does that mean?
See, you may have two root loci branches coming and intersecting at some point in the complex plane. You can have that, right? So there is nothing which says we cannot, right? But the only catch is that, as I told, like if you have a breakaway point or a break-in point in the complex, which is complex, right? The conjugate also must be right? But the condition is that like k should be still positive. Of course, if you are considering positive k, right, or negative if you are considering negative k. That constraint we need to always check. Okay.